So I suspect most of you have seen this idea of nested encryption in the context of onion routing. A client multiply encrypts a message that it wants to push through this onion routing network, and then each layer of the onion router strips away one, each onion router strips away one layer of encryption, and the plain text message, perhaps something you're trying to send off to some server, emerges at the edge of the onion routing network. The problem that we ask in this paper is, what exactly is the problem that this nested encryption is presumably a solution to? And I suppose the presumably is the operative word here, because I think until you have formalized this in a meaningful way, you don't really know whether or not nested encryption works, or what properties the encryption scheme needs to satisfy in order for nested encryption to do what you hope that it would do. So we seek here a provable security treatment for this problem, and I'm doing this in the kind of concrete, practice-oriented tradition. So I want a clear syntax and definition for the problem at hand. And once that's done, we want to look at some constructions. I'll explain that Tor's relay protocol doesn't satisfy our definition. It doesn't for the simple reason that tagging attacks are excluded by our definition of security, and Tor's relay protocol is susceptible to them. And then I'll describe an alternative solution that does satisfy the definition, and it's effectively Nick Matheson's design one from proposal 202 from the Tor community. Okay, so when I say I want to give a provable security treatment here, I want it to be concrete and self-contained. In particular, I'm not looking for something in the UC, in the universal composability model, but something that's clear and game-based. It'll be based on indistinguishability. This is the basic problem an adversary faces when it's interacting with one of two kinds of oracles, and it just wants to identify which of the two oracles it's interacting with based on the input-output behavior of those oracles. Indistinguishability is one, and in fact the most popular way that we use to quantify advantage, the adversary's advantage in distinguishing these two oracles, is just the probability it says 1 when it interacts with one world, minus the probability it outputs 1 when interacting in the other. Perhaps the main idea here is simply to view the problem that nested encryption aims to solve as a flavor of authenticated encryption. Authenticated encryption is by now a very well-known primitive in which you're trying to simultaneously achieve privacy and authenticity. That is ostensibly what's going on in these protocols. The Tor relay protocol, for example, adds in a bunch of 0 bits and then applies nested encryption based on counter mode. It would, at the endpoint, we check for the presence of those 0 bits. That's the authenticity check, and the nested counter mode is presumably our mechanism for achieving privacy. So who's doing the encryption and who's doing the decryption here? So the encryption is effectively the client, A in this picture, and decryption is then done by each and every node, each and every onion router. There are already lots of flavors of authenticated encryption, probabilistic authenticated encryption, non-spaced, misuse-resistant, robust, all kinds of flavors. And I'm suggesting that the problem that nested encryption solves is yet another flavor of authenticated encryption, and we call it onion authenticated encryption, onion AE. Okay, so I promised a provable security treatment of this problem that I've now named, onion AE. So I like to clearly separate the syntax of the thing that we're trying to define from the security definition. So what is this thing just as a simple syntactic object? So it's a 3-tuple of algorithms. There's a key generation algorithm, an encryption algorithm, and a decryption algorithm. The key generation algorithm produces the vector of everybody's keys. So the client here Presumably, his key consists of the collection of all of the individual OR's keys, though that's not actually mandated. And he does the encryption. The decryption is then done in phases, one layer at each OR. Unlike conventional non-spaced authenticated encryption, we're going to need that the encryption algorithm as well as the decryption algorithms are stateful. The strong security notion we're after is not going to be achievable by stateless schemes, and we'll see that later. After we define the syntax of any cryptographic object, we normally specify the correctness condition for it. And I want to do that quite explicitly here, and we'll see why later. Correctness is simply asserting that no matter what key you choose over here, no matter what sequence of messages you feed to the encrypting party, if you faithfully relay the ciphertexts through our OR network, you'll get back, well, m equals m prime for each message. You'll get back the sequence of messages that you initially encrypted. You'll never get back this distinguished symbol bottom, which is used to indicate an authenticity error. Okay, so that's the syntax, and how then do we formalize security? So it looks rather like non-spaced authenticated encryption or almost any of the other AE flavors. Our adversary here is imagined to be interacting in one of two worlds. On the left is the kind of real world where it has an actual encryption and decryption pair of oracles. The encryption oracle is doing something like that nested encryption operation, and the decryption oracle, well, it's emulating what happens at a particular OR. So the adversary identifies which OR in the chain that it's targeting, that's this index I, and then the ciphertext that it's feeding it, and it gets back whatever the algorithm dictates should be returned. This is the real world. We would like this to be indistinguishable from an ideal world whose behavior is very simple. Whatever you ask to encrypt, it produces random bits. Whatever you ask to decrypt, well, usually it produces random bits too. But at the very edge of the network, at the nth OR, we're going to assume a fixed length sequence of ORs. At the very end, it would produce, instead of random bits, the indication of a failure, of invalidity. This is a kind of utopian definition in the sense that if you stopped there, you could easily distinguish the real and the ideal worlds. This is typical when we do indistinguishability-based definitions, that we have to add in some extra little bells and whistles to effectively forbid the trivial wins, to ensure that the adversary doesn't get credit for them. What makes this setting unusual, I think, compared to other authenticated encryption goals, is that it's annoyingly difficult to describe just what it is that those trivial wins are. Okay? And that's because we have this whole chain of ORs, and each of them is maintaining state. And there are kind of obvious attacks, but putting down formally what those obvious attacks are and excluding all and only them is really unpleasant. The idea that we pursue here is to automatically exclude the trivial wins. And when I say automatically, I mean you exclude all and only the wins which are unavoidable by virtue of the correctness condition. I just described to you the correctness condition. So usually correctness only plays a role for saying, what's the functionality of your protocol? If you decrypt something you've encrypted, you have to get back what you started with. It's a functional requirement. But here now, I'm going to use correctness as an integral part of giving the security definition. The basic paradigm is that you give a utopian game, like the one depicted here, that is not achievable due to the correctness condition. And you effectively factor out those wins that are unavoidable by formalizing the correctness condition and automatically adjusting the game accordingly. And this idea is which logically precedes this paper on onion encryption, unfortunately is published just after. That'll appear in a separate paper at Crypto in a couple of weeks. So we call this idea indistinguishability up to correctness. And we start off with our indistinguishability game, the adversary trying to distinguish some real from some ideal game, with indistinguishability defined in the normal way. And we modify it by automatically silencing all of those queries that we somehow are obliged to do something about because of correctness. When exactly do you silence? Silence means instead of answering this yi value, we answer some distinguished value that says, I'm not saying. You silence when for every scheme pi in the class of correct schemes, the response is the same. It's determined by the transcript that's already gone of communication between the adversary and that oracle. The adversary's been having a conversation with the oracle. If at some point in time what the oracle answers is that which it's obliged to answer by virtue of correctness, then instead of answering as you would like to, you replace that response by some distinguished value, I'm not saying. That's the idea. Here then is the utopian game for onion authenticated encryption. This is the full form with all the silly details, like ensuring that you set up the key before you start encrypting and decrypting. And this is everything. It, together with the correctness condition, then serves as an input to that oracle silencing idea, and out pops your definition. What would this look like without the oracle silencing? So in some sense, we're kind of lucky because there was independent work going on we recently learned about, presented at Eurocrypt a couple months ago by De Gabriel and Martijn Stam. And they set out to solve essentially the same problem. They wanted a game-based formulation of the problem that nested encryption solves. And I've clipped the games from their paper. This looks pretty bad, but this is only the beginning. There are the rest of them. Okay. So I believe this seemingly simple idea really helps to radically simplify the games you're trying to understand when the context gets just a little bit more complicated, something like onion authenticated encryption. Oh, seems to have a little out of order. There's a bunch of limitations I want to acknowledge right off. What I've described so far only includes the outbound messages. You need to add in more stuff to take care of inbound messages coming in over the same onion routing network. I haven't included the possibility of corrupted ORs. That seems very strange because, of course, onion routing is largely about ensuring that you maintain privacy despite some subset of the onion routers being corrupt. We haven't included in our modeling this leaky pipe idea that appears in Tor, where sometimes the length of the sequence of ORs you're passing through is 3 and sometimes it's 4 or something like that. Okay? It always has fixed length in our treatment. And then I think the most interesting branch, the most interesting choice we had to make was that we check all of our authenticity at the time of exit, when you're just about to leave the network. This is the same choice that was made in Tor's relay protocol, but it's not the only possible choice. You could instead have said, once a message gets inserted into this onion routing network that's wrong, you should stop it at your first opportunity. It shouldn't traverse the network. These two different flavors of onion routing can both be formalized in in this oracle silencing paradigm, though in the PETS paper we only formalize the time of exit formulation. I don't really know which one is better, and I think it's an important question that those doing concrete onion routing have to face as to which flavor of onion routing they're after. I'll mention that once you add in the extra layer of encryption that effectively goes on, by the TLS record layer, you're not actually getting, in Tor, something like this time of exit authenticity checking. You actually are getting the stronger form, apparently, of authenticity checking associated to eager authenticity. Just a little bit on constructions. As I said, Tor's relay protocol doesn't satisfy our definition, and it doesn't for the simple reason that tagging attacks are excluded by this strong definition of security. Quite informally, tagging attacks are a consequence of using a malleable encryption scheme, and authenticated encryption is invariably stronger than non-malleability as a requirement. It implies non-malleability. We do have a construction, as I mentioned, and it consists of nested encryption. But the kind of thing that you're nesting is not a conventional symmetric encryption scheme. It's not something like counter mode. You need a much more powerful primitive. Here, what we're using is a wide block pseudo-random permutation, a wide block cipher, and it has to be tweakable, in fact, which means that there's this additional parameter which impacts the behavior of the wide block cipher as though it were a separate key. So we do the nested encryption, having added in redundancy. You check it at the edge of the network, and then you tweak according to the ciphertexts that have been output so far at each layer in the OR. Okay, just a few take-homes I want to emphasize that there's importantly these two different variants of Onion AE, whether you're checking at the very edge or constantly as you traverse the network. I think that's an important axis of comparison that hasn't been discussed much. There's a much more recent proposal than the one that we've analyzed, proposal 295. We've looked at it quite recently, and I can't tell you whether it does or doesn't satisfy this definition of Onion AE. It's not at all obvious. And finally, I'll ask whether any of this actually matters for a construction like Tor. And I guess my answer would be to ask a Tor person whether the tagging attacks matter. This seems to be something that hasn't been entirely closed on within that community. From my point of view, it's really nice when you build your protocols from primitives that have some kind of understood security property. And here, we're trying to get to what understood security property nested encryption might have if you implement it well.
Speaker. Questions for Phil, or does anyone from Tor want to answer that last question? Staring at some Tor people, other Tor people, Nick.
Sorry for being so far away from the logical place for a microphone. I think this is a kind of question that we can only really figure out in dialogue with cryptographers like you, because we sort of know what we want from an engineering point of view. The big trade-off on replacing the relay crypto is performance. If there were a widely believed to be strong, definitely and definitely fast white block cipher that we could, tweakable white block cipher that we could drop in, then we would love to use it. Most of the ones we've seen seem to have performance problems on one platform or another, but we haven't tested out everything.
Yeah, so I'll mention that one of the problems with this scheme I've suggested is that this object E is really not a standard cryptographic primitive. This is the complete set of constructions that I know that have been offered for it, and I don't know that any of them are particularly mature or efficient.
Other questions? Okay, I'll throw one. So I really like the Oracle silencing trick, so that's cool. But I have a question. So in the Oracle silencing trick, you basically, in the real world, you check whether the output would be the same for all queries, for all transcripts up till that point for all correct protocols. And I'm worried, might it be possible that the adversary could construct a sequence of queries for which, say, the fifth output would always be the same, but there's no way to know that yet, right? Because the real world might only be able to learn that later. And so it couldn't output the silence symbol.
So the silencing, as I've described it here, is defined in this very existential way, and that would seem to be a problem. That can it even compute whether or not this thing should be silenced? And something I glossed over is that in order for this notion to be meaningful, you need to check that the silencing actually is computable, that function can be efficiently computed. And in order to accomplish this, you typically have to recharacterize when silencing happens, and you end up with a complicated game nonetheless. So this serves as a kind of simple descriptive language for the definition, but you're not done, unfortunately, at that point. To really do anything productive, you'll have to check computability, you'll have to worry about things like whether or not transcripts are arising, in the ideal game, which could never arise in the real one.
Great, thanks. Oh, pass the mic back.
I was wondering if you tried to find a definition that was kind of the weakest that would provide what somebody might want out of nested encryption. And if you were willing to satisfy a stronger definition, could you do it with a more standard, more widely available construction? Like, for example, why not just nest standard authenticated encryption?
So in answer to the last question, why not nest standard authenticated encryption? This would cause a length increase with each hop, and we kind of took it as a requirement that we wanted the ciphertext to stay constant length regardless of the number of hops you went through. The other part of the question, whether or not one might have done better in terms of efficient constructability of schemes if you targeted a somewhat weaker goal, that's certainly possible. Nonetheless, the space between, you probably really want non-malleability and authenticity. We don't, even in the conventional symmetric encryption setting, have interesting examples that sit between there. You can construct artificial examples that are, in that space, but we don't know how to achieve like non-malleable symmetric encryption any more efficiently than authenticated encryption. And my guess is that there's not a big gap there in terms of the efficient constructability of schemes. If you do try and target non-malleability as your basic goal and not authenticity, I believe you'll end up with a much more complicated definition than overshooting and trying for authenticated encryption's counterpart.
Okay, I'm afraid we're out of time, so let's thank the speaker again.